Welcome. Today we're going to be looking at the notes worksheet entitled The Other Four Trigonometric Functions. And up to this point we've spent several days working on the graphs of sine and cosine and working on a bunch of applications with them. And so what we're going to do now is take a look at the behavior and the graphs and the characteristics of the other four trigonometric functions. So tangent, cotangent, cosecant, and secant. And so we'll look at some of those characteristics and do a couple applications along the way as well. So let's start it out here. I have investigation number 1 on your sheet, and we'll work with y equals tangent of x first. If you do get an opportunity, everybody, can you make a z-trig window for me? And let's go 4 units, or 4 tick marks, I should say, going out to the right, and then 4 tick marks, please, going out to the left. Just remember, on this coordinate plane, each tick mark would be pi over 2. So this is pi over 2, pi, 3 pi over 2, and 2 pi. And then working backwards or clockwise, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And so what we'll do is just grab the calculator and kind of graph it, and then match that to what we know about the behavior of tangent, and it should make sense pretty nicely here. So I'm going to grab my graphing calculator and bring it on up. And let's go ahead and go to the y equals. Please make sure you're in radian mode if you get an opportunity. And so I'm going to go ahead and type in y equals tangent of x, and I'm going to hit zoom at the top, and then number 7, please, the z-trig window, of course, and we end up getting something along these lines right here. And so you see a couple things. First and foremost, this graph is different than what we've seen for sine and cosine. The nature of the curves are different. And you also see that it's not continuous. Right away here I've got this part of the curve right here, but then I have this vertical boundary line, or a vertical asymptote, at one of the values. So I'll tell you what, why don't we start at least with the process of putting in the vertical asymptotes, and then we'll go from there. So I see one at the first tick mark, which would be at pi over 2, and we'll talk about why that is momentarily. I also see one 2 tick marks away from there. That would be at 3 pi over 2. And I'm hoping you agree with me that obviously tangent is periodic, so I would get one at 5 pi over 2, or 7 pi over 2, or 9 pi over 2, etc., etc. And working clockwise, think about it from the unit circle perspective. That's kind of a nice way to think about it. But at negative pi over 2, negative 3 pi over 2, etc., etc. And if you remember, think back, of course, to a couple of the representations, specifically the unit circle. Can we take the tangent of pi over 2 the way we defined it? No. Can we take the tangent of 3 pi over 2 the way we defined it? No, certainly not. So that's why those vertical asymptotes pop up. Well, let's go ahead and just sketch kind of the remaining pieces, and then we'll talk about that behavior as we go through and do some of the characteristics as well. So we kind of get this piece right here, a 0 right in the middle, and then going upward from there, and kind of like that. Again, if you have your graphing calculator handy, you probably have this as well. Looking something like this. You could probably even do a better job than I'm doing up here. But basically something along those lines. And that would be y equals tangent of x. I won't go into too many of the details in terms of the point plotting, but let's at least talk a little bit in generalities here. I think we do know in the first quadrant, and that would be from 0 to pi over 2, tangent is positive. And we know tangent increases from 0 to 90 degrees, or 0 to pi over 2. So that's the behavior right there. Tangent is negative in the second quadrant, everyone. So you can see here's the negative aspect of it. Tangent of pi is 0. And then in the third quadrant, everybody, this would be from pi to 3 pi over 2. Tangent goes back to being positive. So you can see positive, negative, positive in quadrant 4. Tangent, of course, is negative. So all of the issues that we've been developing over the last several weeks, and the behavior of the tangent values in particular, show up nicely on the coordinate plane right here. Okay. Well, let's do a couple things in this with these characteristics I'm just kind of looking at on my board. Let's do this. Let's get the vertical, well, actually no, let's get the domain first. Just kind of thinking out loud with this. And it's not all real numbers. That's definitely one major difference between tangent and the sine and cosine graphs. The domain, of course, is not all real numbers. I have to exclude pi over 2, and 3 pi over 2, and 5 pi over 2, etc., etc. Well, what I want to do is just have a way to represent that mathematically. And this will be the first time kind of seeing this. Once you get the hang of it, it'll flow a little better for you. But I guess here's how I would argue it. we of course see that pi over 2 is excluded from the domain. So just on your paper, write that. X can't be equal to pi over 2. But also, again, what we want to do here is include the fact that this occurs, well, I won't go into what it occurs just yet, but it occurs at 3 pi over 2, and 5 pi over 2, and 7 pi over 2, and back again, negative pi over 2, negative 3 pi over 2, et cetera, et cetera. So what we want to do, rather than listing them all, because quite frankly, there are an infinite number of vertical asymptotes here, what we want to do is express it mathematically. And here's, I guess, what I'm hoping you would agree with me on. That our vertical asymptotes repeat every 2 tick marks on this window, right? From here to here, from here to here, from here to here, et cetera, every 2 tick marks, which means they repeat every pi units. And so what we're going to do is write it this way. We have one at pi over 2, and then every multiple of pi before and after that. So we have this k value for, showing up for the first time, and k is basically an integer to kind of tell us that we're dealing with multiples of pi from here. So what it basically comes down to, it's a mathematical way to represent the fact that we have one at pi over 2, and every pi units after it, and every pi units before it. So that's how you're going to express it, and you'll get used to that. Okay, range, everybody. Range is a vertical thing, and I'm going all the way down to negative infinity. We've seen that, and I'm going all the way up to positive infinity. So in terms of the outputs, notice that the range is all real numbers. Perfect. Now, period. Remember, period of your basic sine and cosine function is 2 pi, not with tangent, as a matter of fact. If you look at the graph, I always start from the y-intercept. Here's my y-intercept right here, everybody. How many units do I have to go out to get to the exact same spot? It looks like pi units, 2 tick marks on the coordinate plane. And so as a matter of fact, it's pi units. So we can think about it from the unit circle perspective. And if you have your unit circle, you can grab it and watch this occur. What I would ask you to do is find any point on the unit circle and then go halfway around the unit circle. And if you just go halfway around the unit circle, you end up getting the exact same tangent value. So sine and cosine repeats every 2 pi units. Again, you can really think about it from the unit circle. But tangent repeats every half unit circle, or every pi units. Good. All right. Vertical asymptotes show up where the domain is, or the values are excluded from the domain, so we would just write it like this. And then the zeros, we'll talk about this last characteristic as well here. Zeros of the function are the x-intercepts. I have one at 0, 1 pi, 2 pi, 3 pi, 4 pi, and I hope everybody agrees with me that, the first one that you see probably is 0, and then it repeats every pi after that and every pi before that. Negative 1 pi, negative 2 pi, negative 3 pi. So we're going to do something very similar to this. Here's how we're going to write it. And we don't need the 0, by the way. So here's the first one, which is 0. We can write it if you want, but basically it's going to be 0 plus every multiple of pi before and after it. So you could just write it as k pi. And so this k is basically going to be an integer, meaning it'll take on negative 1, negative 2, negative 3, 0, 1, 2, 3, et cetera, et cetera. So if you want to put the little 0 plus out in front, that's perfectly fine. In this case, it is not necessary because it's 0. All right, so it takes a little time to develop the first one, but let's see if we can roll a little quicker on maybe the second and third and fourth and take care of the remaining 3 here. Let's go with cotangent. All right, everyone. You owe me a z-trig window just like this. Give me 4 tick marks to the right and left. And just kind of think about cotangent. We didn't investigate it in tremendous detail, but you should know where cotangent is positive or negative, and then we can talk a little bit about general behavior there. So let's go for it. I'm going to bring up my graphing calculator again, everybody. Go to my y equals, and I'm going to type in 1 divided by tangent of x. So remember the relationship here on these secondaries being reciprocals. And you could probably just take graph and notice, similar to the tangent function, looks like those curves are decreasing over the interval as opposed to increasing, and our asymptotes are in different spots. But otherwise, it's got the same feel to it. So it looks like I have a vertical asymptote at 0. I have one at pi, And if I asked you to actually find the cotangent of 0, you would tell me it's undefined based on the way we have defined all of these functions, cotangent in particular. And so cotangent is undefined at negative pi and negative 2 pi, et cetera, right through there. And again, what we found basically is that the curves kind of going from infinity to negative infinity, let's just make sure I'm able to get that correct, something like this, et cetera, all the way through the interval there. So take a moment, if you would, and graph those. We'll just have a quick discussion on the general behavior there, and then we'll set the characteristics in place. So, of course, everybody, if you take a look at this piece, here's the first quadrant from 0 to pi over 2. Cotangent is positive, just like tangent. Pi over 2 to pi, everybody. Second quadrant. Tangent and cotangent are both negative, so it goes positive, negative. Third quadrant, of course, tangent and cotangent are positive. So here we go, from pi to 3 pi over 2. Cotangent is positive. And in the last quadrant, from 3 pi over 2 to 2 pi, as you can see, cotangent is negative, just like we expected. Tangent increases, cotangent, being the reciprocal, decreases. And that's the situation. We'd love for you to maybe work a couple things on your own here in terms of these characteristics, but I don't mind talking you through some of the premise here as well. So it looks like with the domain is not all real numbers, we're excluding some. And as you can see, in this case, it's just reverse of what we saw last time. I'm excluding 0, I'm excluding pi, I'm excluding 2 pi, negative 1 pi, negative 2 pi, et cetera, et cetera. So x can't be equal to any multiple of pi, including 0 pi. Range, again, it looks like from infinity to negative infinity there. Absolutely, the range is all real numbers. Period, it's not ideal going from the y-intercept here because, you know, I do have this undefined situation, so maybe just seeing it from here to here. But regardless, if you go 2 tick marks out, you're in the same spot on the graph. So I am hoping you see that the period would be pi units, again, or 2 tick marks on this z-trig coordinate plane. Vertical asymptotes pop up where the domain values are undefined, so x equals 0 pi, x equals 1 pi, et cetera, et cetera. And then the zeros of the function, or the x-intercepts, again, just kind of change from tangent. We have one at pi over 2, and then pi units later at 3 pi over 2, and then pi units later at 5 pi over 2, et cetera, et cetera. So this would be pi over 2, and every multiple of pi before and after it. So again, just you'll have to get used to that k value. All it just says is it's going to repeat every pi before and after our number. All right, 2 down there, guys. Very nice. Just getting a good feel for each of these. They kind of work in pairs. Sine and cosine really look alike. Tangent and cotangent kind of have the same feel, and you'll see the same for cosecant and secant. Okay, so cosecant we're going to do a little more with, just a touch. I'll ask you to go ahead and get the 4 tick marks going. And then give me a 1 right up here and a negative 1 right down there, if you would. And then I'm going to ask you to very, very lightly on your paper sketch the sine function for me, and you're going to do it dotted. So remember the relationship. Cosecant is the reciprocal of sine. And so what we're going to do is take all of those sine values and flip them. So let's do this. I'm going to do it dotted up here. So the sine function, if you remember, starts at the midline, goes up, then comes back down, and then comes back up, kind of like that right there. That's one iteration in the sinusoidal loop. Okay, now kind of working backwards, of course. Something like this. Try to do it as best as I can. There we go. Not too bad, all things considered. So what we're going to do now is take every one of those infinite values on this sine function, and we are going to take its reciprocal. We're going to flip it. And think what happens when we flip them. So let's start out with just a couple ideas initially. What happens when I flip the sine values of 0? Well, here's sine of 0. Sine of pi is 0. Sine of 2 pi is 0. What happens when I try to flip 0? Well, it becomes undefined. So think about this. When sine is 0, what do you think is going to pop up on the cosecant graph? We'll see that in just a sec. Positive and negative should show up as well. So sine is positive in 1 and 2. Cosecant's going to be positive in 1 and 2. Sine is negative in 3 and 4. Cosecant will be negative in 3 and 4. How do we flip numbers, guys? Well, when we flip numbers that are in between 0 and 1, like flip 1/2, flip 1/3, flip 1/4, the smaller the number, when you flip it, the larger it gets. So think about that, and we'll see if the general pattern works with our logic here. All right, well, let's go for it. Let's give it a try. So I'm going to go back to my y equals. You guys do the same and clear that out. And everybody, if you would, please type in 1 divided by sine of x. And we end up getting something like that. Now, I'm going to hold off graphing that for just 1 sec. I also want to just very quickly, and you don't have to do this, just kind of peek at the screen here. I'm going to also put in the sine of x, and you can see there it is. So here's the sine function, and the cosecant values are basically taking the reciprocals of all those. So we get this defined u in between two different asymptotes. That's basically how it works here. All right, well, let's give it a try. Let's graph it on here. So remember, and we kind of talked about this, wherever sine is 0, well, flipping 0 makes it undefined. And so you end up getting vertical asymptotes. So if you're unsure if you can picture the sine graph, you could probably really picture the cosecant graph nicely. Anywhere where sine is 0, cosecant has a vertical asymptote, of course. And then by flipping all these numbers right here, it kind of comes down. Let's make sure I get that right. So something like this. Not parabolic, because it's going towards the asymptotes, but it definitely has that U-shaped feel to it. And then something like this as well, going downward. And the quadrants should still make sense, where sine is positive, cosecant is positive, or sine is negative, cosecant is negative. That would be our case right there. All right, let's fill in our characteristics. Let's take care of that, and then we'll go hit secant. Okay, so let's talk domain. In this case, I have some exclusions, of course. So wherever sine was 0, cosecant is undefined, so I have a vertical asymptote popping up at 0, and at pi, and at 2 pi, etc., etc. So by now, being the third time, I'm hoping that you understand that notion right there. All multiples of pi are not part of the domain for the cosecant function. Now this is a good one right here. I'd love for you to pause the video for just a sec, see if you can come up with a range, and think about it in reference to the sine function, what its range was, and then flipping all those numbers, what's the range of cosecant? Well, basically what I see, everybody, is the graph is only defined from 1 and above, or from -1 and below. That's it. You're not seeing anything in between. The in between would be the sine function. So this, everybody, happens to be your range. Anywhere lower or equal to -1, or anywhere above or equal to +1. And those are your two intervals. Good. It's kind of on the outskirts of those sine values. Period, guys. If the period of sine is 2 pi, then the period of cosecant is 2 pi. You're just taking the reciprocals. And you can kind of see this piece right here. From here, well, we get another one, and we would start our u going upward right here. So period is 2 pi. Vertical asymptotes, this is fairly simple as it ties into the domain, getting one at all those multiples of pi. And here's a great one right here, everyone. Based on the fact that I have a u going upward, and then here I'm getting a u going downward. Any zeros? No, absolutely not. So if you kind of go back, and I'll go back so we can really see it nicely on the graphing calculator there. Let's get rid of that sine function. Any zeros at all? No, of course not. The graph's never touching the x-axis. All righty, everyone. 3 down. And then 1 to take care of there. As I said, cosecant and secant kind of go together. So let's go get this one right here one last time. And as long as you're understanding really that the behavior of what we've been talking about now for several weeks sort of comes to fruition here in each of these 4 That's the most important piece. I'm not going to make you point plot these or anything like that, but you should be comfortable with their characteristics and so forth. So I guess what I'll ask you to do is the same exact thing, please. So 1 and -1 right there. And then very, very lightly and dotted, if you would, can you draw me the cosine function? So cosine is the one, if you remember, max to max. So something like this. And doing the best I can up there with my wave. Down it goes on the other side here. And think about it here. To get the secant values, we're going to very simply flip all of the cosine values. And so think what would happen specifically when cosine is 0, like at pi over 2 and 3 pi over 2 and so forth. What happens there? Flipping 1, by the way, I didn't say this on the last one, but when you flip 1, you still get 1. So if the secant of 0 is 1, then let me say that again. If the cosine of 0 is 1, then the secant of 0 is going to be 1. All right, well, let's go ahead and just check that out. Probably have a good sense of what it'll look like. Let's just confirm that idea. So I'm going to do 1 divided by cosine of x. Hit graph. Same thing. Obviously, I'm going to go ahead and just go back real quick and put cosine of x in just to kind of see them together. But obviously, those secant values are just the reciprocals of the cosine values. All right, let's put them in. So here we go, everyone. Vertical asymptote wherever cosine is 0. So right there and right there, right here and right here. That looks great. And then just flip the cosine values. The smaller the cosine value, the larger the secant values. That's how reciprocals work. So kind of a u right there and a u there. And just for our purposes here, it ends, obviously, theoretically we would have a dot, 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 and we would get another u there. But we're just going from -2 pi to 2 pi. So something like that and something like that, approaching each of those vertical asymptotes. Perfect. And now at this stage, let's get the remaining characteristics on this one and put it all together. But visualization, hopefully you're really seeing where these values are coming from, as we have taken a lot of time to develop them in this course. So let's see, domain. Well, wherever cosine was 0, secant is undefined. So that's at pi over 2 and 3 pi over 2. But again, I don't want you to write it like that because there are an infinite amount of them. So every multiple of pi after and before pi over 2 units. So pi over 2 plus k pi. I'm hoping everybody agrees that the range is the same as last time around. Anywhere lower than -1 inclusive, and anywhere above +1 inclusive. Period, just like cosine, everybody, period's 2 pi. Vertical asymptotes, now we're getting into a rhythm with this. Of course, right where the domain values were excluded. And zeros, nah, not a single one. And there are your 4, everybody. So again, what you're responsible for is not the point plotting piece, but understanding, being able to envision it, being able to see some of those values. If I showed you one as opposed to the other, you should be able to tell me which is secant, which is cosecant, which is tangent, which is cotangent, and you should be able to tell me the characteristics. So those are your responsibilities for these other 4. Let's do just a couple examples of this and then see where that leads us. So example 1 says use a graphing calculator to determine the following information for the given function. And so just, obviously we had comprehensive sine and cosine functions. We could create more comprehensive other functions, tangent, cotangent, cosecant, and secant. So I'm going to actually ask you to pause the video for just a couple minutes there and run all of those on your calculator and see if you can come up with each individual characteristic. Just, a little gauge for you to see if you're on the right track with this. And then come on back and then I'll walk you through. It'll be at a fairly brisk pace, having the expectation that you've done it. Okay, well, let's see how you did, everybody. So I'm going to bring my calculator up, and let's go on back here. And I'm going to type in 1/2 tangent 2x. And I'm going to hit graph. And remember, the larger that number is in front of the x, the more horizontally compressed it is. And I know it's not ideal, but it looks like, just from my perspective, it looks like starting from here, we only have to go one tick mark out for the period. So here to here, it looks like it's repeating. And so in this case, I'm getting a period, everybody, of exactly pi over 2. Now, you don't have to write this on your paper, although I would probably say it's a good idea. If you remember with this, this would be the b value, right? Of course, the b value is the coefficient in front of the independent variable. Well, remember, for sine and cosine, the period is 2 pi over b. Well, in this case, everybody, for tangent, it's not 2 pi over b, it's pi over b, because your basic period for the tangent function is pi. So it's pi over b. And then hence, that's where we get that answer over there. So pi over 2. Good. Letter B. I have, let's see, let's go on back here. And again, you're checking your answers, hopefully, and if anything is off, you'll let me know about it. So sine of x and then plus pi divided by 2. So it looks like in this case, let me make sure I've typed that correctly. We have that typed in. And let's see, we're looking for the vertical asymptotes here. And I'm getting 1. Here's a vertical asymptote at pi over 2, and then every pi from thereafter. So I'm seeing vertical asymptotes at x equals pi over 2 plus k pi. Now, just one thing to note about this graph, and then I'll go right on to the next one. That should look familiar. We kind of talked about the relationship of sine and cosine. One is just a horizontal shift of the other. So this is cosecant of x plus pi over 2. Isn't this, everybody, exactly what you saw for the secant graph? Isn't this really just secant of x? So again, cosecant and secant very simply are just shifts of one another. So this really is, I'm just going to write it here, you don't have to. This is y equals secant of x. All right, let's go on to that next one. Go on back. I've got 1 divided by, and then tangent x minus pi. Close that off, hit the graph, and that looks good. So this would be a horizontal shift to the right pi units. And it's interesting on this one, just kind of viewing it. Does everyone see the graph that we drew for just y equals cotangent of x? Isn't it virtually identical? And because if you move it pi units to the right, it's the same exact graph. And so anyway, we get the same zeros that we got before. I saw it as pi over 2 and then plus k pi. Okay, great. Let's go get 1 or 2 others here. So next one for me is 1 divided by cosine of x. Then you're going to have to close that off because then we're going to add the 3. And I'm going to hit graph right there. You know what? We're going to have to change our window just a little bit. We didn't catch the top part. So I'm going to go up a little more. I'm going to go, let's see if that catches it. Yeah, that's a little better. So sorry I didn't give you a heads up on that piece, but if I'm looking for the range, it just basically took the secant functions and bumped it up 3 units. So instead of the low point, or I should say really instead of going from -1 below, now it's 1, 2, 3 up. Now it's from +2 below. And instead of from +1 upward, it's 3 up now, everyone. So it's 1, 2, 3. It's from 4 up. So it looks like we are below -2. Oops, sorry, let me just make sure I have that right. I think I said below 2. So y is less than or equal to 2. But also, I'm also seeing that as y is greater than or equal to 4. Let me just check that one more time to be sure. So here we go, everybody. Here's a y value of 2, and we're below that. Here's a y value of 4, and we're above that. So it basically took the -1, and again, don't write this on your paper. It took the -1 and the 1, and it shifted those up 3 units. So that same type of range. All right, let's do these last 2 rather in a hurry here, and then I can get to the last one of the day. So y equals sine of x, does it have any vertical asymptotes? No, 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 no. Absolutely not. Continuous across the board there, domain's all real numbers. Secant of x, does it have any zeros? No, 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 of course not. And so we have that piece. So hope you did okay with those. If you have any issues with interpreting what the graphing calculator has given you, you'll let me know. Let's do the last one here, if that's all right with you. Example 2, just a nice little quick function with one of these other 4. I don't want to give too much away here. So let's see what we have. A plane is flying at an altitude of 5 miles over level ground, and it's going to pass directly over a radar antenna. Let d be the ground distance from the antenna to the point directly under the plane, and let x be the angle of elevation to the plane from the antenna. D is positive as the plane approaches the antenna. So I guess what we have going here, I'm going to try to draw this out. That's a good looking plane. So we've got the plane going this way, kind of like that. And then we have a radar antenna right down here. Oh, that's beautiful. So we have our radar antenna right here, and it's going to be 5 miles above that radar antenna. So let's see, I've got that right there. And then I have the ground distance from there to there, basically. So 5 miles above, and I have my ground distance, and then everybody, x is my angle of elevation right in there. Okay, and it says write d as a function of x. And so what we have here is, it looks like a nice right triangle drawing. What's interesting about this perspective, though, is it's more dynamic in nature. That airplane is moving, so the right triangle is going to change, obviously, as that airplane moves. If that airplane is moving and the triangle changes, then x is going to change, and the ground distance is going to change. And the way we're going to write it as, the ground distance is dependent on the angle of elevation, d as a function of x. So I guess I'd ask you to just go back to a little right triangle trigonometry and start out with the basic equation. Here is my angle of elevation right here, everyone. And in my right triangle, it looks like I have an opposite side that's constant, and I have the adjacent side, which is the variable. Opposite and adjacent, everybody, is tangent. And so I'm going to write this as tangent of x equals the opposite side over the adjacent side. Now, I do want to be a little careful with this. It does say write d as a function of x. So what that means, everyone, is it's d equals. And so, guys, what I'm going to do is very simply remedy this by taking this d and multiplying it out of the denominator up to the numerator. And in the same breath, if it's okay with you, I'm going to go ahead and bring this on down and divide by tangent of x. So I'm hoping everybody agrees with this as a function. X is my input, d is my output, and there's the mathematical relationship relating the two. I suppose we can write this another way. I'm thinking out loud with this. You have it on your paper already. But remember, dividing by tangent, and that's how we're going to put it in the calculator, by the way, is the same as multiplying by cotangent. So, I don't know, that looks pretty good too. So you can see, they're essentially, again, interchangeable, tangent and cotangent. But that would be the relationship right there, either dividing by the tangent function or multiplying by the cotangent function. It looks like I asked us to just graph the function over a quick interval here from 0 to pi over 2, and is it reasonable? Well, let's see. So let's kind of talk about this piece real quick. Pi over 2 radians, again, I'm just going to write this as 90 degrees right here. And so this is basically going from 0 degrees to 90 degrees. And think about, well, if the angle of elevation is 0 degrees, that's all the way out here. The plane's all the way back. And as it gets big, or it gets closer and closer to the radar, I'm hoping everybody is in agreement with me that the angle of elevation is going to get closer and closer to 90 degrees, until obviously it's right above the radar, and then that angle would be 90 degrees. And think about what the distance would be at that particular point. Let's just see if it bears out mathematically. We'll just take a moment and do this and then wrap this on up. So I'm just going to do 5 divided by tangent of x, and I'll just hit graph here. And we just wanted it from 0 to pi over 2. If I wanted to change my window, I definitely would to see it in a little more detail. But basically here you see it as x is small. So if I have a small angle, it looks like the ground distance is pretty large. And that makes sense. The airplane's very far away. As x increases, the ground distance decreases, of course. So the ground distance is getting smaller and smaller and smaller. Everybody, what happens at exactly pi over 2 or at 90 degrees? What's the ground distance? 0. And then what theoretically happens here, everybody, is it just starts going further and further because it's going to the left now, and direction matters. We would consider the direction to be negative, and it's just going to go further and further and further away to the left. Okay, well, long story short there, is it reasonable? Sure, most definitely. Okay, so again, just understanding the characteristics of the other 4 trig functions. We'll have one more day, I think, kind of doing a review of all 6, putting it all together. But again, no point plotting, that's the good news. But you should be comfortable with understanding the behavior of our values, the graphs of each you should be able to recognize, and then apply those characteristics. Please let me know if you have any questions along the way.